Okay, morning everyone. Thanks for coming from this little rainstorm. Let's get started. Again, our homework too will be due on this Friday. I've seen some, in my office hours, seeing some students and showing their code and showing great progress. Again, we have the office hour every weekday. Please feel free to seek for help if you need it. And I also see some messages asking, could we release homework 1 grade and to make sure that your decision tree implementation is correct or not. So our TAs are working hard to do this. And I think right now, at least 60% or 70% of grades have been done. But it's still, if you cannot see your grades are available, you can come to the TAs and ask for the solution. But the key problems here. So even if you could get your homework 1 graded, for example, there might be some problem in your decision tree implementation. TA won't tell what's the tiny bugs in your implementation. Right? They cannot debug the code line by line for you, right? So in other words, if you want to make sure your implementation is correct, you can't get any detail from the grading results. Instead, I would suggest you first, you need to double check your implementation logic is consistent with our lecture. And if you're not sure of this, welcome to bring your laptop and to our office hours and let either me or our TAs to check your logic, right? At least we can double check your implementation if it follows the logic in the algorithm table we listed in the lecture slides. But after that, if there's still some problem, there's still seems your running results are not reasonable, there must be some a tiny bugs or subtle bugs which you made, but it may not be very easily to identify. In such case, that will require your patience, right? Because even I were you or TAs were you, in case of such kind of situations, we have no choice. We have to debug step by step. And I think the most efficient approach, which I have told several students who came to my office, is that you start with a very small toy data set. You can even fake a small data set by yourself. Then you debug one by one. Don't hit and run and look at the final results. I think most of you are using Visual Studio or VS Code, right? Those kind of IDEs have the functions that you can do the debugging step by step. You can look at every step, what's the variable name and what's the variable value. You just need to make sure on very small data set or small toy data set, you look at every step, what is your intermediate variable values, the weighted error, right? The alpha t, beta t, those kind of stuff are doing correct. And it's consistent with it's supposed to be. And once you can, you can go through this whole procedure just for once, and then most likely you will identify all the bugs, and then you can make it work. Right? So this is the typical procedure. But don't expect that, okay, TAs or me will help you to do this step-by-step debugging. That's not our job, right? We're assuming that you have some basic implementation skills and algorithm development skill. Basically means that once we give you such an algorithm table, you are able to implement it and make it work properly. Okay, that's why we kind of highly suggest everyone, if you need the help, just come to the office hour, so that we can double check, at least from the algorithm perspective, it is consistent. And also we can point out several commonly mistakes we haven't seen so far, so to avoid you making those mistakes again, right? And then the remaining things are kind of subtle issues, which will require you a little bit more patience, but you do have enough time to do that. Does it make sense? Any questions so far? Okay, I hope this suggestion will help. Okay, so let us continue with agnostic learning. Right? So for quick review, in the last lecture, we talked about the tail bounds, right? The tail bounds we're using here is called Hofstad's inequality. Right? So Hofstad's inequality can upper bound on how much the average of a set of random variables differs from the expectation, right? So here P can represent the mean of a random variable, right? So which we call true mean or true expectation. For example, if you just toss a coin, right? You know, the underlying nature of this coin will have some kind of probability. You see it heads or see it tails up, right? And this is called true mean. And on the other side, we might do this random tossing experiments many times, like independent many times. Each time I just look at the outcome, which is either tail or head, right? And then I take the average of those observations together, which we call empirical mean, right? This P bar. Empirical means actually is computed based on the average of a set of independent trials, right? So empirical mean essentially is a random variable, right? Like if we write it in a more formal way, suppose we do m random trials, meaning that we have observed the values for m random variables x1 and xm, right? All those random variables are independently, identically distributed, right? They have the same mean, have the same distribution, but they are observed independently mean that we're doing those experiments for independent multiple times, right? And then then I take the average of those m independent random variables and use it as my empirical estimate of the true mean of each random variable. Okay? This is called empirical mean. And the true mean is computed, or it is inside each random variable. Okay. And then we would like to know, what's the chance that the true mean is epsilon away from your empirical mean? Does it make sense? Okay. Remember, empirical mean here is the average of random variables. It's still random variable, right? So that means this random variable, it still has some distribution. It is random. So it's possible that our true mean is close to this random variable. Or it's possible that this true means, I mean, although it probably is more rare, but it is possible that this true mean is quite away from this random variable, right? That's why we have this Hofstad's inequality. Actually bounds the probability that your true mean is epsilon away from your empirical mean, right? And this bound tells us that given specific epsilon, the probability that your true mean is epsilon off away from your true mean, your empirical mean, will be no bigger than this exponential term. Right? So if you look at this upper bound, this exponential term, it is e to the power of -2 m epsilon squared. Right? So you see this bound depends on two things, right? First, it depends on how many independent random variables you're going to average to get the empirical mean, right? And second, it depends on how much offset you will set, right? Epsilon. So see that this probability upper bound decays very fast along with the increase of m and epsilon, right? So basically means that, okay, the more independent random variables you average, this averaged random variable is more stable, right? It's more stable and is more likely to be very close to the true mean. But just be aware, no matter how many random variables you're going to average out, this average random variable is still a random variable. It still has a distribution, right? Does it make sense? Right? This is a set of random variables. You do the average, right? A set of random variables, you combine them together, still random variable, right? So this basically means that, okay, the more random variables you average them together, this average random variable, it will become more and more stable. It becomes more and more closer to the true mean. In other words, the most of their probability mass is staying in the region is very close to the true mean. It won't be jumped too far away from the mean, right? And there is another factor which determines this bound is epsilon, right? So epsilon tells us, okay, how far away from the average random variable to the true mean of those random variables, right? So you can see that if you set a large epsilon, this upper bound will decay very, very dramatically fast, right? So the decay is like exponentially and quadratically fast. So basically means that the more farther away, or the further away from the true mean, the much less likely your average random variables will take value at that place. Does it make sense? Any questions so far? I hope everyone will get sense about this, right? Okay. So basically, this Hopkins equilibrium tells us, okay, if you just average a set of IID random variables together, your average random variable will get very close to the true mean, and also it will be quite stable. It won't be jumping around. Okay? It will be very stable to be surrounding the true mean and not far away. That's basically what this Hopkins equality wants to reflect. Okay. Any question? Okay. So now we want to apply the Hopkins inequality to derive the relationship between the training error and test error, or the generalization error, right? So how can we apply that? If we look at agnostic learning setting, right? So what's the setting of agnostic learning? What's the feature? What is the key feature of agnostic learning as compared to our previous discussion? Yeah, exactly, right? Exactly. Training error is not necessary to be zero. Why? Because agnostic learning make a much more realistic assumption that your, so maybe I should write something here. So your learning algorithm will have some hypothesis space as your search space, right? And as we mentioned many times, the so-called learning essentially is to search over this hypothesis space, find out a hypothesis which best match the training data, right? And agnostic learning just do not make any strong assumption about whether your target function f belongs to your hypothesis space or not, right? So remember, in our previous discussion, we're assuming f is essentially inside H, so that for any training set, right, for any possible f, we guarantee that we can find a hypothesis with zero training error, right? That's kind of too strong, right? In many practical cases, you won't guarantee that, okay, you sometimes, many times you even don't know which type of target function, which family of functions your target function belongs to. Right? So this, to be more conservative, to be more realistic, you cannot make assumption that your target function must stay inside a hypothesis space, right? It is possible that your target function stay outside a hypothesis space. That means like no matter how well your algorithm is, right? Even in your hypothesis space, you find a hypothesis which is closest to the ground truth, there is still some kind of gap. Right? This gap will lead to the result that there must be some training data set, the prediction of your closest hypothesis, and the prediction made by the ground truth won't completely match, right? Which implies non-zero training error, right? So this is called agnostic learning setting, right? So the key to the agnostic learning setting is that, okay, we can no longer assume you always get zero training error. You could have like a non-trivial training error. Then our goal is that, okay, suppose I accept such kind of imperfection. I have some like imperfect hypothesis space, and I can get non-zero training error. Can I still derive something about the generalization error? And even better, if we can say the generalization error is still relatively small, then that's good, right? So that's the key, or that's our objective for agnostic learning. So now we want to leverage the half-density equality to derive the relationship between your training error and our generalization error. Right? So the key observation here is we can find that the empirical error or the training error essentially is just empirical mean of the true error, right? So how can we see that? If you look at the computation of the training error, you can view it as an average of a set of binary random variables, right? So remember when you do the training prediction, right? You use your hypothesis, your learned hypothesis, to make prediction for every training example. And if your prediction is different from the ground truth, you will have an output 1, right? Otherwise, you have output 0. And now you can imagine you have a bunch of 1s and 0s for your prediction over the training set. Then you just add up all those 1s together, all the 1s and 0s together, and divide it by m. That's how you compute the training error. And for every particular training example, whether you make an error or not, this is a binary random variable. Why is it a random variable? We know that when we look at our prediction is correct or not, we'll either have 1 or 0, right? It's a binary. But why is this a 1 or 0 is a random variable? Any thought? Any guess? Yeah, exactly, right? Yeah, because you see, this is an indicator, right? This is an indicator. 1 or 0 indicates whether you make a wrong prediction or correct prediction, right? But this indicator is based upon xi, right? Xi as a training example is randomly drawn from some complex data distribution, right? So this indicator essentially is a function of a random variable. Remember, a function of random variable is also a random variable. Does it make sense? Right? The xi itself, it comes from the training set, right? But xi itself is a random variable. Why? Because we're assuming that our training set is randomly drawn from, yeah, it's RID. Yeah, we're assuming it's RID. Right? Each xi is drawing from some data distribution D from our setting, right? Of course, we're assuming the training set, each training example, our RID drawing are independently identically distributed, right? And that's why we could say like each of the individual binary indicators are RID random variables, right? And then we just test our prediction on every training example. We got every binary indicator variables, and we average them out to get our training error. So you see, this is essentially an empirical mean, right? If you look at the true error or the generalization error, right? It is the probability that, okay, for any sample X, which is joined from the data distribution, what is the probability that your prediction by H is different from prediction by the ground truth function or target function F, right? So this probability P essentially is the mean of every indicator random variable. Why? Because for any binary random variable, its mean is the probability that random variable takes value 1. Does it make sense? Right? For any binary random variable, right? If you have like say y, right? Y is either 1 or 0. Then what's the expectation of y? Or what's the mean of y? Oh, that's the empirical estimate, right? Like if you observe y many times and then you take the average, right? This is empirical. But if I ask you to compute what's the mean of y or what's the expectation of y, how do you compute that? And what is it? Yes, right? If you just do some calculation, you will see that the expectation of y, sorry, please forgive my awkward drawing. The expectation of y is simply the probability that the y is 1, right? Let's just follow the definition, right? The expectation of y is 1 times p of y equals 1, right? Plus 0 times p of y equals to 0, right? Of course, 0 multiply anything is 0, right? So your expectation of y end up being the probability of y takes 1, right? So if you look at the true error or generalization errors definition, the generalization errors definition is the probability that this binary indicator variable is 1. In other words, it is the expectation of each binary indicator variable, right? Does it make sense? Any questions so far? Right? So that's why we could say like error DH, this generalization error, essentially is the true mean. And training error is the empirical estimate of the true mean, right? If you take a look at here, right? This is the average of a set of binary random variable. And this guy, the generalization error, is the true mean of each binary random variable. So we can directly apply Hopkins inequality. Does it make sense? Yeah, any other questions? I want to make sure everybody did capture the K. Keep on here. Right. Everyone feels comfortable? Mm-hmm. No, you don't. You cannot compute. The true mean, you will never be able to compute that. Right? Because you need to know what's the data distribution here, right? You can't do that, right? You don't know what the data distribution is. It's not normal, it's not gamma distribution. You don't know. It might not be written analytically. What we can do is just we can compute the training error, right? Because every time you just okay, you learn a hypothesis, you just use your hypothesis to predict every training examples, you know what's the training error, right? But for the true mean, which is actually the expectation of each binary random variable here, you will never be able to get exact value, right? So we want to use this half-density inequality to find some kind of relationship between the training error and the true error, so that we can give some kind of rough estimate about the true error based upon the training error. Does it make sense? Any other question? That's a very good point. In other words, like if we really are able to compute to the true mean, the generalization error, then why do we apply those kind of like similarly sophisticated inequalities to do these things, right? We just look at, okay, what's the generalization error? I would like know that, and then I say, okay, this they can use that to compare different learning algorithms. Everyone's comfortable? Okay. So now we know that the true error is the true mean here, and the training error is the empirical estimate to the true error. Then we directly apply half-density inequality. There's nothing need to change. We could claim that the probability, the generalization error, is epsilon away from the training error will be upper bounded by e to the minus 2 m epsilon squared, right? So again, m is the number of the training examples, because m is number of binary variables you want to average out, right? Average out means that how many training examples you want to look at, and look at 1 and 0 and then average them out, right? And epsilon indicates how far away you want to look into the difference between the true error and the generalization error, right? And ideally, we want our true error to be close to the training error, right? We want our generalization error to be close to the training error, right? So that's why we don't want this upper bound to be large, right? You want this upper bound to be as small as possible, right? Okay, but let us continue, right? This is just a continuation of our discussion in the last lecture, right? So right now, directly application of the half-density inequality can give us the result that for any particular hypothesis H, the generalization error of H is the probability that this generalization error is epsilon away from the training error is upper bounded by this guy, right? But when we look at the behavior of learning algorithm, we know that learning algorithm is possible to use an arbitrary hypothesis as the learning outcome, right? So then we should have a have a more general statement about the generalization error learned by the learning algorithm, right? So in other words, we want to look at the probability that there exists a hypothesis in the hypothesis space whose true error is epsilon away from the training error. How do we extend our probability bound for a specific hypothesis to the probability bound for the existent statement, right? So for this, for the former, we have already got that, okay, for a particular hypothesis, okay, this is a bound that is probability of the true error epsilon away from the training error, right? But in general, we would like to say, okay, what if there exists a hypothesis in the whole hypothesis space whose true error is epsilon away from the training error? We want to bound this probability. So we know there's some difference here, right? This is the same as we have used that to derive our previous sample complexity bound, right? So the idea is kind of similar to what we have done before. We use the union bound, right? So for the existent assumption, that basically means that, okay, if there exists a hypothesis whose true error epsilon away from the training error, that basically means that the first hypothesis in the hypothesis space is epsilon away from the true error, training error, or the second hypothesis in the hypothesis space whose true error is epsilon away from the training error, or the third one, blah, 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 right? So you can see that this existent statement corresponds to an event, which is a union of event across every individual hypothesis in the hypothesis space. And then we know from the union bound, the probability of a union of set events is less than or equal to the summation of the probability of each individual event, right? And the probability of each individual event correspond to a specific hypothesis, which we have already derived the upper bound, right? With Hopkins inequality. So basically we just add all those bounds together. And for every particular hypothesis, they have the same upper bound. So we add them together, you basically just multiply by the size of hypothesis space, right? So now we get our result, right? By leveraging the union bound, we can immediately derive that the probability of existing hypothesis in hypothesis space whose true error epsilon away from the training error is upper bounded by the size of hypothesis space times e to the power of -2 m epsilon squared. Right? This is the same derivation procedure for the consistent learner. We have done that before. Right? So again, remember our motivation. Our motivation is that, okay, we hope our training error is sufficient or enough to represent the generalization error. In other words, we hope our generalization error to be quite close to the training error. We don't want to say the case that, okay, you got 0.01 training error, but your generalization error is 30%. That's too bad, right? So we want to make some kind of control, right? We want to make some control that this kind of things happen, the chance to be very small, say to be less than some given threshold delta. And how can we control this? To control this, because we have already known there exists some hypothesis whose true error is epsilon away from the training error is upper bounded by this guy, right? So we want to this probability of this event to be less than or equal to some given threshold. To make it, we can make its upper bound to be less than or equal to delta, right? And then we can solve the inequality for this upper bound. Then we just do it, right? And solving this is pretty straightforward. You can rearrange this and you can immediately get that when m, the number of training examples, bigger than this guy, then the upper bound of the probability will be less than or equal to your given threshold, which implies that the probability there exists hypothesis whose true error is epsilon away from the training error will be no less than delta. Right here gives our results. This is kind of a very similar statement as we did for the consistent learner case where you have 0 training error, right? So we got a sample complexity bound saying that if the number of training examples is bigger than this guy, is that no less than this guy, then we guarantee that with probability at least 1 minus delta, the true error will not off by more than epsilon away from the training error. That means if your epsilon is enough small, then the true error and the training error will be very likely to be close. In other words, your training error can reflect the quality of your generalization performance. Mhm. Yes. Yes, exactly. Right. So now we can take a look at the structure of this bond, right? Of course, number of training examples will be determined by like what's the offset between true error and the generalization error, and also what's the threshold of the probability, right? And also what's the size of hypothesis space, right? So intuitively, the more training examples we use, the more representative of your training set to cover the data distribution, right? Then your learned hypothesis will be your learned hypothesis when it is evaluated on this training set will be more reflective of its generalization performance, right? And here, from the Hopkins inequality and the union bound, we can derive some quantitative measurement of the sample complexity. We see that, okay, when M is no less than this lower bound, then we can make sure that with high probability, how high the probability, at least 1 minus delta, and your true error will be close to the training error. And how close it is measured by this offset epsilon, right? And of course, this lower bound of the number of training examples will be determined by how closeness you want your true error is to your training error, and how much probability you want this to happen. Right? It determines by delta, right? And meanwhile, we could see that it is also determined by how complex your hypothesis space, right? Does it make sense? Because it has a logarithm of size of hypothesis space. Right? So the larger the hypothesis space, meaning that the larger of this guy, even given the same closeness metric epsilon and confidence metric delta, right? The larger the hypothesis space indicates that the more training examples you need to do to achieve this kind of closeness under this confidence level, right? And this is again justifies the Occam's razor principle, right? And if you can make your learning algorithm to always guarantee the same training error, right? And then given same epsilon and given same delta, of course, the simpler hypothesis space will require you a smaller number of training example to achieve that. Okay. Any questions so far? Okay, great. So now let us explain the structure of this sample complexity bound one by one, right? So again, the epsilon here in the denominator indicates the difference between the generalization and the training error, right? So it's not the absolute level of the generalization error. It's just the distance between the true error and the training error. And your generalization error, you can roughly view as training error plus this epsilon, right? Right. And this epsilon indicates how much worse will the classifier be in the future than it is at training time, right? So this is a big difference from the consistent learner case, right? In the consistent learner case, we're assuming the training error is always 0. So epsilon actually indicates the absolute value of the generalization error, right? Like 0.01 means that, okay, my generalization error is really 0.01. But here in the agnostic learning case, because we cannot make sure that your training error is 0. So we can only tell that, okay, what's the chance that your generalization error is training error plus 0.01. This is what we can do. Okay? Because you don't know what's the training error you will get. Any question? Okay. Hopefully everybody will get a sense of this, right? Because of the nature of agnostic learning, there's no guarantee that your training error will be 0. So what we can say about the guarantee for the generalized error is that, okay, what's the likelihood, what's the chance that your generalization error is just 0.01 bigger than training error, or 0.05 bigger than training error. We can give that kind of bound, but we cannot say, okay, the generalization error has a large chance to be less than 0.01. Why? Because I don't have the guarantee about the training error. My training error will, if it is already being 0.05, then we cannot say the generalization error will be less than 0.05. Okay. Okay, the second thing, again, this is just emphasize again the usefulness, the Occam's principle, right? So we say this sample complexity bound is also determined by the log of size of hypothesis space, indicating that a smaller or simpler model assumption will reduce your sample complexity given the same epsilon and delta. Okay. And in other words, Occam's principle favors simpler hypothesis space, right? and the last one is about this delta, right? Of course, you want the probability that your true error and the training error to be as close as possible. You want this probability to be large. Then you need more training examples. Okay? That's why this delta, the smaller delta is, the larger the probability that they're close, and then the more training examples you will need. Okay. Explain what? Okay. So suppose you got two hypothesis spaces, right? And you have some kind of learning algorithm for each hypothesis space. And you can guarantee for this data set, for the same training data set, you got the same training error. Okay. So now we would like to say for a particular epsilon and delta, meaning that I want my true error to be epsilon close to the training error. And I want this probability to be like 0.99. That means I can set some epsilon delta here, right? And then I would like to say, oh, okay, under which hypothesis space I will need more training examples, right? This can be reflected by this lower bound, right? And for the same epsilon and delta, and for the same training error, of course, the smaller hypothesis space will have a smaller sample complexity, right? You don't need to collect that many examples. You can guarantee your true error will be epsilon within epsilon from the training error with that probability 1 minus delta, right? That make me feel better, right? Because you don't need like labeling costs or whatever other costs to collect more training examples. That's why we favor, that's why Occam's principle is useful, right? It's valuable. Any other question? Great. Very good point. Okay. And in addition to the sample complexity, we can also try to switch epsilon and m here. And now epsilon, because it represents the offset or difference between the training and test error, if you switch them, you can immediately derive the so-called generalization error bound. This generalization error bound tells you that how much the true error will deviate from the training error with high probability, at least 1 minus delta. It tells us if we have m examples, right, arbitrary m examples, right, then with probability at least 1 minus delta, the difference between the generalization error and the training error will be upper bounded by this guy. So this is basically, you just take the square root of these things, and you get this one. Okay? And this actually is a very, very important. And later we'll discuss how this one can motivate a new type of learning algorithm called SVM, right? But here we just want to emphasize the structure again, right? So for any particular number of training examples, right, with high probability or at least 1 minus delta, the generalization error will be less than or equal to the training error plus this term. So you can see that this term is determined by the number of training examples, the probability level delta, and the size of hypothesis space. Right? So you can see that the more training example you have, the gap between the generalization error and the training error is smaller, right? On the other hand, the larger the hypothesis space, the larger the gap. So you can see there's another way of the justification of the Occam's razor principle, right? If you use a simpler hypothesis space, you can make the gap between the generalization error and training error to be smaller, right? Given the same training examples and given same delta, right? Any question? Okay, if we just look at this inequality again, right? So this inequality tells us, okay, with probability at least that 1 minus delta, the generalization error is less than or equal to training error plus the right-hand side, right? So if you give the same m, if you give the same delta, then the larger hypothesis will lead to a larger gap between the generalization error and the training error, right? And the smaller hypothesis space, of course, will have the smaller gap between the true error and the training error. You got a question? This one? Okay, so okay, let us assume, okay, this is your training error, right? This is your training error, right? This inequality basically tells that, okay, how much larger will be your true error from the training error, right? So this gap between the true error and the training error is upper bounded by the right-hand side term, right? So the right-hand side term just tells us that, okay, if you fix m, you fix delta, then the larger the hypothesis space, meaning the larger the log of size h, then the larger the gap, right? And if you choose the simpler hypothesis space, meaning this logarithm h is smaller, right? Then the gap is smaller, right? And then that means, okay, your generalization error will get closer to the training error, right? It will be more reflective, it will be more representative by the training error. We have a closer estimate or more accurate estimate about the generalization performance according to your training error. Does it make sense? Yeah. Any question? That's a very good point. Okay. So far we have introduced the general framework for the agnostic learning, right? If we make a comparison between the consistent learning, which we discussed previously before the Forbic, and the agnostic learning, we see some like very interesting similarities and dissimilarities, right? So for the consistent learning, where we assume your true error, your training error is always 0, right? And then we can claim that when the number of training examples is bigger than this guy, then with high probability, at least 1 minus delta, your true error will be less than epsilon here, right? However, for the agnostic learning, you can see the sample complexity have a very similar structure as the consistent learner case, but the meaning is different. The meaning is that, okay, when your number training example is bigger than this guy, right? And we can claim that the training error, the true error, will be epsilon, will have the high chance to be within epsilon distance from the training error. Okay. So it's basically, you can say the training, with probability at least 1 minus delta, your true error will be less than or equal to the training error plus epsilon. Right? It's not directly epsilon, it's just plus epsilon. Does it make sense? Right? So agnostic learning just tells you, okay, how closeness, how tightness from your training error, from your true error to your training error. Okay. Any questions so far? Mm-hmm. Mm-hmm. Well, the case, the thing is that in real world, the data is not distributed uniformly. The distribution is highly complicated. It's much more complicated than a uniform distribution. Yeah, in many cases, like you probably you are not even able to represent this distribution in some like closed form equations. That's why we have to, I mean, to be as general as possible, right? We have to assume, okay, there must be some complicated distribution, and however, we cannot access the probability density function of that distribution. We can only draw samples from that distribution. Yeah, of course, you can simplify this problem by assuming, okay, my data distribution is just uniform and just calculate these things. And yeah, of course, you can do that, but it's not as general, is just not as general, sufficiently general to be to be a theoretical framework which covers all kinds of different cases. Another question? Okay, so now it looks like we have a nice framework, right? We covered the ideal case for which you have a zero training error every time, or more realistic case in which you don't have a zero training every time. But in that case, we can still derive some probability estimate about the generalization error according to the training error, right? And then the question is, have we solved everything? Are those sample complexity bound or generalization error bound are enough to deal with all possible situations? In what? Mm-hmm. Yeah, it covers the cases of like agnostic case, right? It covers the possibility that, okay, your target function is outside a hypothesis space. But is this current bound good enough? Shall we consider a more complex case? You just I just request ask your like thinking, right? While thinking, you don't need to any thought? Okay, let's think about, right? For both cases, right? For the sample complexity bound, when we use logarithm of size of hypothesis space to indicate the complexity of your model, right? A machine learning model. Is this okay? It's not okay, right? Because these are assuming that your hypothesis space is finite, right? You can take a logarithm of hypothesis space to reflect the complexity of your hypothesis space, right? But as we previously discussed, right, even many hypothesis spaces are infinite. Even for linear classifiers, the hypothesis space are infinite, right? Why are linear classifiers hypothesis space is infinite? Yeah, exactly, right? Remember, for linear classifier, you have to define the weights, right? The weight vector for every feature and also for Bayes term, right? Those weight vectors are consist of continuous values, right? So you have infinite possible continuous values. So that basically means your hypothesis space is infinite. When hypothesis space is infinite, can we calculate logarithm size of H? We can't, right? Because the size of H is infinite, right? What's the logarithm if it's not meaningful? And unfortunately, most of machine learning algorithms, they have infinite hypothesis space. That means this sample complexity bound, although it is more general, it consists more realistic case, do not apply to most machine learning algorithms because the hypothesis space is infinite. You cannot calculate this guy. So actually, we have not addressed everything, right? At least we need to come out some kind of sample complexity bound for infinite hypothesis spaces, which are used by most machine learning algorithms. Then we could say, okay, for different machine learning algorithms, what's the estimate of number of training examples would we require to achieve some kind of epsilon and delta, right? Or we can compare the sample complexity between different learning algorithms, right? So obviously, we're just in halfway, right? So now let us look at how do we address the infinite hypothesis space issue, right? So our previous analysis was restricted to finite hypothesis spaces, right? But when we switch to infinite hypothesis spaces, is there any difference, right? Suppose I have two infinite hypothesis spaces. Can we tell there's still difference in terms of expressivity? The answer is yes. Even spaces A and space B, they both are infinite and uncountable, but you can still tell, like say A's expressivity is bigger, is higher than B. So here we give some example, right? We can consider three infinite hypothesis spaces. Right? The first one are rectangles. And the second one are 17 size convex polygons. And third one are general convex polygons. Right? So I want to ask, no, these three hypothesis spaces, every space is infinite, uncountable. Right? Now my question is that which hypothesis space do you believe is the most expressive? Which? Why? Yes, that's what the intuition tells us, right? And let me be more concrete. You can view like, okay, for every possible element in the rectangles, right? It must belong to the general convex polygons, right? So it means every element in rectangle hypothesis space will belong to the general convex polygons. However, if you do this opposite statement, that is not true, right? You can pick up some like a convex polygon, which might be octagons, right? It doesn't belong to rectangles. Similar observation applies to the 70 size convex polygons, right? Every possible 70 size convex polygon will also belong to the general convex polygon, but vice not versa. And the second case we can consider is like consider linear threshold function, which is just linear classifier, and a combination of linear classifiers. Again, both spaces are infinite, uncountable, but linear classifiers obviously are a subset of a combination of linear classifiers, right? Because a single linear classifier can be viewed a combination of linear classifiers with only one in a combination, right? But it's not, but vice not versa, right? So you can see that even you have like different hypothesis spaces, and every hypothesis space could have infinite candidates or elements, right? You can still compare their expressivity, their complexity, right? Then the thing is, the question here is that how can we come out a metric which can characterize the complexity or the expressivity of those infinite hypothesis spaces? From that metric, we can compare them. We can directly do comparison. So to do this, we're going to introduce a particular and very famous metric, which is called Vapnik-Cherev-Nanky dimension. Briefly speaking, it's VC dimension. Okay? And the VC dimension is such a metric which can be applied to infinite hypothesis spaces and give you some quantitative metric reflecting the complexity of that hypothesis space. Okay? So a more formal definition of VC dimension is that VC dimension is a measure which measures the expressive capacity for a set of functions, right? Remember, each set of functions can be viewed as a hypothesis, right? And once you get VC dimension, right, you can use the same, almost the same trick like Hopf inequality, like union bound. You can apply them all of them together. You can derive the sample complexity bound and generalization error bound using the VC dimension. The technique is the same. Like here, we're gonna meet those subsequent procedure. We'll only introduce the concept of VC dimension. Okay. So to be more concrete, we want to use this learning rectangles as an example to illustrate why measuring the complexity of the infinite hypothesis space is important, right? So assuming we want to learn a target function, right? This target function is presented here. It's a rectangle classifier, right? And this rectangle classifier will classify all the points inside as positive and all the points outside as negative, right? So imagine how would our learning algorithm will learn a rectangle classifier closer and closer to the ground truth, which is this rectangle, right? When we increase the training examples, right? So at the beginning, you might just have these 3 training examples, right? And your learning algorithm will return you this small red rectangle. And of course, because this low sample complexity, the learned rectangle is far away from the ground truth, right? But when you increase the training examples, say you add 2 more positive examples, your learned rectangle grows and get much closer to the ground truth, right? The ground truth, again, the ground truth is this rectangle outside, right? So you can imagine that as you add more and more training examples, although your learning algorithm is always searching over this infinite hypothesis space. Remember, this is a rectangle hypothesis space. It's infinite, uncountable. But guided by this more and more training examples, your learned rectangle is still getting closer and closer to the ground truth. So that's actually give us the intuition that, okay, even for the infinite hypothesis space, there is still a way to measure the sample complexity, tells us, okay, how far away, given some closeness between the ground truth and our learned hypothesis, how many training examples would we require? That's what we want our VC dimension can give us such a hint, right? Once we give this VC dimension, which measures the complexity about your rectangle hypothesis space, we want to derive such a sample complexity bound. It tells us, okay, say we use like 100 mol training examples. It will guarantee with large probability your learned rectangle will be epsilon away, will be within epsilon from the ground truth rectangle. Okay. That's the motivation. Okay, so now to introduce VC dimension, let us think about how do we look into, or how do we investigate the expressivity of a type of functions? Okay. Let us consider you got 2 points in a plane, right? And I want to use linear classifiers to classify these 2 points. Okay. And of course, for different possible labelings for these 2 points, if you want to correctly classify these points, you're going to use different linear classifiers, right? Now, for 2 points, we have 4 possible labels, right? So here we only consider binary classification, right? We can label this point as positive, negative, and all these 2 points as negative, and one positive, one negative, one positive, and all positive, right? We have 4 possible labeling scheme, right? And we find that for all possible labelings of these 2 points, we can find corresponding linear classifiers which perfectly classify every label, right? So this is called shattering, right? So we say linear functions are expressive enough to shatter 2 points. In other words, shattering means that given a set of points, no matter what possible labeling you assign those points, I can find a corresponding classifier in my hypothesis space which correctly predict every label of those points. If we can do that, we claim that, okay, our hypothesis space can shatter this set of data points. This is our definition. Does it make sense? Any question? And then in the 2-point case, right, we can claim that when our hypothesis space is linear functions, then our linear function hypothesis space is expressive enough to shatter 2 points. Why? Because for every possible labeling for these 2 points, there are 4 possible cases, right? And for every labeling scheme, we can find a corresponding linear classifier in my hypothesis space which perfectly predict those labels. That indicates that, okay, our linear classifiers are expressive enough to shatter 2 points, right? So now let us proceed to more points, for example, 14 points. Now I want to ask, is a linear function hypothesis space, linear classifier hypothesis space, expressive enough to shatter the 14 points? Is it or not? No, why? Mm-hmm. Yeah, Exactly, right? So remember the shattering requires that, okay, for every possible labelings, right? And for some simple labeling like this, yeah, I can find a linear classifier which perfectly separate positive and negative examples, right? However, if I put more complicated case like this one, right? You won't be able to find any linear classifier that correctly predict every label, right? That's not possible because the classification boundary is not aligned. Yeah, we'll talk about the solution later. Here we'll just introduce some kind of like a measurement to measure the expressivity about your hypothesis space. Okay. And for this case, like if you put a more complex label in this case, you cannot use linear classifiers to classify them, right? That means our linear functions are not expressive to shatter 14 points. And then what kind of classifiers or what kind of hypothesis space can shatter 14 points? Exactly, right? That means we need to seek for more expressive hypothesis space. For example, the 14 polynomial functions, right? So here, I will just give you a more complex hypothesis space like polynomials. And then you can show that for arbitrary labeling over this 14 points, you can always find a smooth curve which shatter them, which correctly predict every label, right? So now we'll give a formal definition of shattering. Right? We say a set S of examples is shattered by a set of functions H if for every partition of the examples in S into positive and negative examples, there always exists a function in H that gives exactly these labels to the examples. So basically means that, okay, if you just label those set of examples arbitrarily, for every possible labeling, I'm gonna find a hypothesis in my hypothesis space H such that that hypothesis can correctly predict all the labels. Right? If your hypothesis space can do this, then we claim that your hypothesis space H can shatter S. Right? And from this definition, and from the concrete examples I'm showing, we can immediately get the intuition that a rich set of functions can shatter a larger set of points, right? The richer your hypothesis space, the more likely you can shatter more data points, as the case for the 14 points, right? For the 14-point case, if we just limit our hypothesis space to be linear classifiers, that means just lines, right? You won't be able to shatter that many data points. However, if I extend richness, right? I extend my hypothesis to be polynomials. Remember, polynomials also include linear classifiers, right? Polynomials just means your linear classifiers, the polynomial order is just one, right? But if we can make it richer, means that I can allow higher order polynomials in my hypothesis space, then we can immediately shatter these 14 data points. Okay? In other words, shattering can reflect the complexity of your hypothesis space. Okay, so let's stop here today. And on next Tuesday, we're going to go through several concrete examples, and we can manually calculate for each particular hypothesis space how many data points they can shatter, so we can have like more intuitive and direct experience, and to say which hypothesis is more expressive. And then VC dimension is directly defined on the shattering, the concept shattering. Okay, see you on next Tuesday. Hi.
So when we look at the PAC currently, there's like the log H and the log epsilon inside.
Mhm.
Yeah, so I'm wondering though, what are the base of the log we're gonna use? Is there 2 or 10?
2 or 10, but both fine. That
Yeah.
doesn't matter.
But when we just put a different base in that function and we plug in the number.
You have different number. I
Yeah.
know that. That's fine. As long as you tell us you which base you have used and
Oh,
you write down the procedures. Just do not give a number. If you say okay, the bound is 5.3.
Just
Yeah.
as long as I show the procedure.
Yeah, you show precision is fine.
So in the reality, I think it's highly depends on the size of the data, right? So if the size of data is large, we use log 10, and then otherwise we use 2 or.
Oh no, there's no choice because this bound are just the theoretical guarantees. They won't like they give you some kind of sense, but this bound is a lower bound. It's not actually the real exact number of examples you have used. This just give you a rough estimate. So in
Yeah.
practice, even if you use that for the estimation, they're not just calculating one bound.
Oh,
Like
okay.
you're just calculating. So when you increase m, right,
Mhm.
and you see how this bound varies
Oh.
and give you some kind of trend so that you can give a rough
Okay, so
estimate.
the-
Yeah.
The important part is just a trend, right?
Yes,
So
a trend is
that
not
might
like
be
single number.
before
Yeah.
use, right?
Yes.
Yeah, I got
Yeah.
it. Thank you.
Mhm.